All right, revisiting a projectile. So we have worked a lot with projectiles in Unit 6. So we're going to look at these two equations. It says we've seen quadratic functions modeling the height of a projectile as a function of time. Here are two ways to define the same function that approximates the height of a projectile in meters, t seconds after it was launched. Okay. So here we have a quadratic function in standard form. And below it, we have a function in factored form. And it says they're the same function, but how could we test to see, are they really the same function? So there's a couple different ways. One way is we could multiply this back together to see if we got that. And one strategy is the box method. Another strategy is distributive property. So you may have used these strategies in the past. If we multiply them together, we have to be very careful to distribute the first term to both, and then distribute the second term to both factors. Both terms in the second factor. When we multiply it out, we end up getting what we started with in standard form. Right? So here's factored form, multiply it out, we end up with standard form. Same thing here. These two terms are like terms, and they add up to 27t. So we end up with the same amount. All right. Okay. So we've seen quadratic functions modeling the height of a projectile as a function of time. Here are two ways. Which way of defining the function allows us to use the zero product property to find out when the height of the object is 0 meters? Well, in order to use the zero product property, it really tells you exactly what you need. You need something equal to 0, and you need to have a product, which is things multiplied. This has a term plus a term plus a term. This has a factor times a factor. So this is our product. So in order to use the zero product property, we need our quadratic to be in this factored form. We want to know when does it equal 0. So we want to figure out when does those factors equal 0. Without graphing, determine at what time the height of the object is 0 meters. So I want you to hit pause and help figure out, when is this going to equal 0? When is this factor going to equal 0? And when is that factor going to equal 0? All right, hit pause. All right, you've already tried this on your own, and you figured out t minus 6 equals 0 when t equals 6. And the other one is a little more tricky. 5t minus 3, we need to set it equal to 0, carefully solve, add 3 to both sides, divide by -5 to get t by itself. So at t equals -3/5 or t equals 6, those are both places that would make this 0. But what does it mean in the context of the problem? We want to know when the height of the object was 0. Does it make sense to talk about -3/5? -3/5. Does that make sense in the problem? Not really, because the object was launched here at time 0, and it launched and then it hit the ground right there after 6 seconds. So really, t equals 6 makes more sense in the context of the problem. All right, sorry, let's clear that off. All right, how did we solve the problem? Well, we set each factor equal to 0. Why is factored form more helpful for finding the time when the object has a height of 0? Well, here is our height, right? Here's our height. This is height, and this is time. And if I want to know when the height is 0, here the height is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, right? Height is 0 right here on the ground. So if I can figure out what my x-intercepts are, that can tell me where the height is 0. What if we tried to solve the equation in standard form by performing the same operations on both sides? So let's say we had negative 5t squared plus 27t plus 18, I believe. If we set that equal to 0 and I subtract 18 and then, I've got t squared and t, it's a lot more complicated and we don't have all the tools yet to do that. So we really need it to be in factored form in order to use zero product property. All right. In an earlier unit, we saw that the factored form of a quadratic expression such as that allows us to see, such as the quantity x minus 5 times the quantity x plus 9, allows us to see the x-intercepts of its graph. But we didn't look into why the graph crosses the x-axis at those points. Can you explain why it does now? This is a great question, right? We kind of just talked about it, right? So it crosses the x-axis at negative 9 and at positive 5. Because if that's when it equals 0, right? It equals 0 at that point, at each of those points, at negative 9 and at 5, it equals 0. All right? Okay. Great. Let's check in. Clear. Okay. How does the zero product property help us find the solutions? It makes it really super easy. We just have to find what makes that equal to 0 and what makes that equal to 0. Can you explain why the solutions to that equals 8 are not 3 and negative 4? This would have 3 and negative 4 as solutions. But if I plug in 3 here, 3 minus 3, 3 plus 4, I would get 0 times 7, and that would not equal 8, right? So we have to be careful. These are the zeros or the roots or the x-intercepts, the solutions to it equaling 0. The expression x squared minus x minus 12 is equivalent to this. Can we apply the zero product property to solve that? Well, it's not in product form, so I can't use this zero product property yet until I put it back into factored form. All right, can we solve that by performing the same operations on each side? Definitely not. We would need to convert it or complete the square or do all sorts of other interesting things before the end of this unit, you will be able to figure out different strategies. But for now, we need it to be in factored form. All right.